All right, in this video, we're going to talk about double replacement acid-base reactions. This is on the back of the double replacement reactions home notes that you guys got on Thursday. If you didn't get these, and if you don't have a printer, unfortunately, you just have to copy down loosely for, yeah. Okay, so acids. You can identify the formula of an acid because acids usually have hydrogen out in front of their formulas, followed up by some sort of nonmetal or polyatomic ion. Also, some acids might have some carbons and hydrogens out in front, and then COOH at the end. So some examples of these acids could be hydrogen bromide, HCl, sulfuric acid, H2SO4. Vinegar is an acid, and it's one of those with a Cu at the end. Vinegar is CH3COOH. So those are just some examples. Bases can either have the hydroxide ion or carbonate ion. They usually have a metal out in front and then the hydroxide. For example, sodium hydroxide, you can have calcium hydroxide. You can have lithium hydroxide. Carbonate bases will have some metal out in front and then carbonate following it up. So for example, sodium carbonate. You can even have baking soda, which is technically bicarbonate, but NaHCO3. Those are some examples. So we're going to talk about acids reacting with hydroxide bases, and then we're going to talk about acids reacting with carbonate bases because their reactions are a little bit different. So the general outline of an acid reacting with the hydroxide base. Now this is a double replacement reaction, so the cations are going to switch with each other, not get together, but switch. So that means the metal is going to get with whatever X is. That's going to make an ionic compound. Of course, we're going to balance the charges for that. And then hydrogen is going to get with hydroxide. So if you think about what HOH is, 2 H's and 1 O, that's water. So this is going to be the general outline. In order to be an acid-base reaction, you have to have an acid and a base reacting, and they will make neutral products, which is an ionic compound and water. So, for example, this is our acid, and this is our hydroxide base. The hydrogen and the sodium are going to switch spots with each other. So that's going to put sodium with chlorine and hydrogen with hydroxide, which is HOH or water. We have to balance the charges of this ionic compound. So looking at your periodic table, sodium is +1, chlorine is -1, so that formula is just NaCl, which hopefully we knew that, and water is just H2O. We should be able to put in states of matter. Sodium chloride does dissolve in water. You can check your solubility chart in case you forgot. Water is a liquid. The last thing you would do is balance this. You have to be careful because your H's come from 2 different spots here. So you have 2 total H's on the left, and you do have 2 total H's on the right. This reaction is already balanced actually with 1, 1, 1, 1. All right, for the next one, our base is actually listed first, which is fine. You don't have to have the acid first. You just have to have an acid and a base on the reactant side to the left of the arrow. So the aluminum and the hydrogen are going to switch spots. That's going to put aluminum with the sulfate ion plus the hydrogen with the hydroxide. Now remember, we don't care about these little numbers. We just care about that H is getting together with OH. That always makes water, no matter what those little numbers are. Now, for the aluminum sulfate, we have to balance charges. Aluminum is +3. Sulfate is -2. So that means we're going to need 2 sulfates and, 2 aluminums and 3 sulfates to balance charges. Let's check if it dissolves in water or not. Aluminum sulfate does dissolve in water, and it will be aqueous. Water is a liquid. You want to maybe try pausing the video and try to balance this. It is a little bit tougher. Okay, so if you already paused it, here we go. I noticed that I have 2 aluminums on the right, so I'm going to need 2 on the left. I notice I have 3 sulfates on the right, so I'm going to need 3 on the left. If I count up my total H's, I have 6 from the acid plus another 6, because 2 times 3 is 6 H's from the base. So that's a total of 12 H's. In order to get 12 H's on the right, I'm going to need 6 waters. So it's balanced with 2, 3, 1, 6. All right, now let's do reactions with carbonate bases. So we still have an acid, this time just reacting with a carbonate base. In double replacement, the cations switch. So that means the metal gets with whatever X is, and then hydrogen gets with carbonate. Now, if you were to look at the charges here, hydrogen is +1, carbonate is -2, and that makes H2CO3. Now, I know it's been a crazy weekend, and we probably forgot all about this reaction, but I said that this compound breaks down and decomposes, and it's a special reaction that you guys have to just straight up memorize. Well, yeah. Well, this breaks down into water and CO2. So we're just going to actually erase this and just break that down into water and CO2. So, we all know that vinegar and baking soda, when mixed, gets all bubbly. That's actually, the vinegar is an acid, the baking soda is a carbonate base. It gets all bubbly because you make carbon dioxide gas. Inside those bubbles are literally the carbon dioxide gas. It also makes liquid water, and you need to check if that's aqueous or solid. Okay, let's get to it. So hydrogen and calcium are going to switch. That means the calcium is going to get with chlorine. The hydrogen is going to get with carbonate. That makes H2CO3, which we are going to just have to straight up erase and turn that into water and carbon dioxide. Coming back to calcium chlorine, we have to balance the charges. Calcium is +2, chlorine is -1, so the formula is CaCl2. Water is a liquid, carbon dioxide is a gas. Let's check the solubility of calcium carbonate. That actually does not dissolve in water. That would be a solid. Oh, it's calcium chloride, sorry. Yeah, that dissolves in water, aqueous. Okay, last thing we do is balance the reaction. I notice I have 2 chlorines on the right, so I'm going to need 2 on the left. And that gives me 2 H's on the left. I have 2 on the right. I have 1 carbon on both sides. I have 3 oxygens on both sides. 2 + 1 makes 3 on the right. So this reaction is balanced. Everything else is a 1. Maybe pause the video and try to do the next one on your own before I go through it. Okay. Hydrogen and potassium are going to switch. That means potassium is going to get with sulfate. Hydrogen gets with carbonate. Remember, that's just going to break down into water and carbon dioxide. Let's check the charges here. Sulfate is -2. Potassium is +1. So this is K2SO4. Let's check if it dissolves in water or not. We'll check potassium sulfate, and it does dissolve in water. So it will be aqueous, liquid, gas. we have 2 potassiums on both sides, 2 hydrogens on both sides, a sulfate on both sides, a carbon on both sides. The oxygens are balanced. Everything is just 1, 1, 1, 1, 1. Okay, so you guys have learned every type of reaction so far. Now they're going to be mixed together, and you're going to have to figure out what the reaction type is and use that pattern to predict the products. So, for example, in this first reaction, I noticed that I have 2 compounds, no elements, just compounds, and they're both aqueous. They're not acid and base, they're just ionic compounds. So this has to be a double replacement precipitate reaction. So in those types of reactions, the 2 metals are going to switch spots with each other. We have to balance the charges when we make compounds. So I check the charge of aluminum, it's +3. Fluorine is -1. So this is AlF3. Silver, that's one you have to memorize, is +1. And nitrate is -1. So that's the correct formula. Now, this is called double replacement precipitate because you literally have to make a solid precipitate. If you don't, there's no reaction. So we have to check our solubility chart to see, does one of these products not dissolve in water? So I'm going to check aluminum fluoride, and I see right away that that's going to be my solid precipitate. If you were to check silver nitrate, remember all nitrates, if you look down that column, are aqueous. All right, from here we balance the reaction. I have 3 fluorines on the right, so I'm going to need 3 on the left. I have 3 nitrates on the left, so I'm going to need 3 on the right. Everything else is just a 1. For the next type, I notice that I have 2 reactants. One of them is oxygen, and the other one is made of carbons and hydrogens. So remember, these are very flammable. Organic compounds are very flammable, and they burn with oxygen. This is combustion. Combustion always makes CO2 and water, which is a gas and a liquid, or a gas, depending on how hot the reaction is. Most likely it's a gas. From here, save your O's for last in the balancing. Maybe pause the video and try it on your own. 3 carbons on the left, we're going to need 3 on the right. 6 H's on the left, we're going to need 6 on the right. Counting up your total O's on the right, I count 6 plus another 3 makes 9. In order to get 9 O's on the left, one of the 9 comes from our fuel, whatever's burning. The remaining 8 need to come from oxygen. So if you have 4 sets of 2 O's, that'll give you 8 O's. This is 1, 4, 3, 3. All right, and the last type, I notice I have 2 compounds. They're both aqueous, so it has to be some sort of double replacement. I'll check to see if it's an acid and a base first, and if it's not, it's precipitate. Acids have hydrogens out in front, so this is actually an acid. But in order for it to be acid-base, you have to have an acid and a base reacting. Bases could have hydroxides, so this is a base as well. So this is going to be double replacement acid-base, specifically the hydroxide bases. The cations are going to switch. Beryllium gets with bromine, and hydrogen gets with hydroxide. Remember, we don't care about these little numbers. Just think about H getting with OH. That makes water, which is a liquid. Beryllium is not on our solubility chart, so it is, we don't know whether it dissolves in water or not. Maybe it does, maybe it doesn't. But we still need to check its charge. Beryllium is +2. bromine is -1. This is BeBr2. To balance the reaction, I need 2 bromines on the left. If you count how many total H's you have on the left, you have 2 plus another 2 makes 4 H's on the left. So to get 4 H's on the right, you're going to need 2 sets of water. All right, this concludes the double replacement acid base. You should now be able to complete your single replacement and double replacement homework and upload that to Schoology.